So the case setup is quite simple. We have a cylinder with the diameter 0.04 meters with the flow velocity at 0.025 meters per second. We're essentially working with the air as a working fluid, hence the kinematic viscosity, the value that you can see here. One of the things that we are interested in with the flow over cylinder case setup is the interval at which the vortices are going to shed themselves. This is the equivalent of shedding frequency that we have at the last year. One of the ways in which we determine this shedding frequency is through the Strouhal number and vice versa. For the case of a circular cylinder, this is a good approximation that we have, the formula that you see right there. Along with that, the Reynolds number, this is a dimensionless number required essentially, which helps us understand the ratio between the inertial forces versus the viscous forces. So once we've done let's say understanding what the problem is about, let's take a look at how does that look numerically. So now that we have a good idea about what the simulation essentially spoke about, let's take a look at some of the results again. Now that we've seen what the vortex shedding looks like, let's take a look at some of the data points that we have. One of the first things that we looked at was the force coefficients that we have, force and moment coefficients. So we can open that .dat file in Excel primarily. So in Excel, you can just convert that into the Excel format and we will have all of these data points that are present right there. In certain instances, you will see something like these. These are just the formatting errors right there. So just select all of the data, come back right here and then have it as a number. You can increase, there we go. So you can increase the data points and then have them available right there. Now, of course, since we don't have three-dimensional data, the side forces, the pitch and yaw roll, the roll and yaw, these data will be 0 since this is just a two-dimensional thing. One of the things that we can do effectively is have plots for time versus the coefficients. So what we've done effectively is we have taken the time step only from 150 seconds, since that's where we were writing our solution from anyway. And logic being that at 150 seconds, you have reached sufficient state of your cylinder that you can now confidently take data points from there, numerically speaking. We can see that the value for coefficient of drag keeps bouncing off between 0.224 and 0.234 as the time passes. This gives rise to a certain conversation about how the physics of the flow is also changing with respect to how your simulation is running in that sense. What we will do is we will add the coefficient of lift plot here as well. Let's take a look at what that looks like as well. So as you can see, we have added the coefficient versus time plot here, the lift and drag being in blue color and lift being in the orange here. We can see that coefficient of lift also keeps, bouncing off between positive 0.1 and negative 0.1 here. This also indicates and sort of reinforces the fact that there exists a sort of periodicity of how fluid bounces around your particular cylinder. This talks about the symmetricity of the geometry that we have taken, and the Reynolds number that we are working with also adds on top of it. So this gives you a confirmation of how the fluid properties are effectively changing on the surface of your cylinder as you are simulating over a particular amount of time. And this data can then be validated with experimental results or published results and so on and so forth. Now let's take a look at the noise data. So here we have something called noise right here. Before I go to that, I'll also talk about the curl point and curl surface. Each of these folders contains data about the pressure, the data. Curl pressure essentially talks about pressure above or below a certain reference pressure. This data is written at a certain position. We can see that right here. And it is given the name observer 0, and from the 100th second time, we are essentially writing the data points all the way till your 200 second mark right here. And this is repeated for individual observer that we have around your particular simulation right there. At the same time, we also have something called curl surface, and on top of that surface as well, we have written this particular data, p curl, and on the geometry, what type of data we have right there with respect to that particular time. So this will effectively give you on top of the surface object file that we have. So through the tutorial files, there is something called surface.obj that is right here. Let's take a look at what that looks like. So I've imported the surface.obj file in my domain right here. You can see this surface.obj is effectively a very simple looking rectangle that we have. What this is or where exactly this is located is in the middle of my cylinder, and on top of this surface is where we will effectively get the surface data of what noise is. What this will do effectively is this will capture all of these data points of pressure and basically compare that with a reference acoustic pressure for the atmosphere and understand what the curl value is for individual time step that we are looking at, and subsequent mathematics will happen with the curl functions, where we will do root mean square and we will have formulas for certain SPL, sound pressure level, or power spectral density, so on and so forth, which will then represent what my noise looks like in this particular boundary or on this particular surface. Now, application wise, we can think of this particular surface object file as something of the sort of a window, let's say. For instance, if this was a side mirror and you had the window of the passenger or the driver, you could see that from the side mirror, if the wind is hitting your particular window right there, what type of noise could be generated due to turbulence in that instance. So this serves that purpose in that instance to explain what this surface level noise is going to be in that object. Let's take a look at that. So what I have here is the noise folder, and I can open the surface noise, import surface, and I'll have the option for FFT as well as the 1/3 octave. Not much difference between the two, only about how we have clubbed the data together and what we want to look at. Let's take a look at the FFT for now. And if I want to take a look at the surface level noise right here, I just need to open this surface.case in ParaView. So I've opened the surface.case right here. Let's just hit apply and we will see what the noise data looks like. So understand that the data points that we had on top of our cylinder are vastly different from what the data points we have on this particular surface level object right here. You will see that the amount of data points we have is 1073, and this is quite more than what we initially started off with. So the noise data that we can see on top of this particular surface can be seen with individual time step right there, right? So what this is telling you effectively in that sense is how the noise is looking like on that particular surface, right? So this is effectively your PRMS. There is also data for SPL or the sound pressure level. This is effectively, measured in decibels, and you will see the decibel level that is present right there. And this data, again, you'll be able to visualize for every so time steps right there. Let's do one thing here. Let's just open this case file and nothing else. All right, much better now. We will see what the SPL data essentially looks like in this instance. This effectively gives you a good idea of, as your vortex shading is occurring on this particular domain, what level of noise is getting generated on top of this particular surface, right? The mathematics behind how this noise is generated, I'll discuss that in just a bit, but this gives a view into the post-processing aspect of OpenFOAM. So for instance, if we were to look at this all-run script that we have right here, What this essentially is doing, the run parallel, is it is just post-processing the data that we had written. And this data that we have written is effectively the curl data present in the control dictionary file in the functions. So in our control dictionary file, we have seen that we were writing certain curl surface. So in the curl surface, we will see, let's say, what type of function this is. This is the curl function on top of the cylinder. This is the speed of sound 343, so to speak, on top of the surface.obj file that we have with a surface type inside. We are using ASCII format needed for your surface level noise, and the values for pressure, what region it is going to be in, by default region 0. Time starts at 100, time ends at 1000, and every 10 intervals it is going to be executed with respect to your runtime. Similarly, for curl point, we have defined 4 different observer positions. These are north, east, west, and south of my particular cylinder. So on top of my cylinder, the 4 different points are located right there. And similar to what we have done with the surface data, we have also given the individual controls right there. There is one final thing that we've also defined. It's called cutting plane. Effectively, what this does is it will write your solution for every so time steps, and it will effectively give it in a VTK format. So the cutting plane folder that we have, a random time step that we have, let's open this VTP right here with ParaView. So this is what you can see with the VTP, and if I just hit apply, you'll see that this is a 2D representation right here. So there will be no X and Y plane, only just the Z plane. And I can just see the data of velocity, what this looks like just for this one time step, 125, right? So if there is a specific data point that you are really interested in and you want to just visualize for that one point, we can use this post-processing function in OpenFOAM to effectively write everything that we require in that sense. This works great for either of the axes, at what point do you want it and in what normal, and you can write the subsequent fields that you are really interested in as well. Now finally, we have the forces and the force coefficients as well. Just on top of the cylinder, we were writing the forces. This COFR here talks about the center of rotation, or essentially the axis which is symmetrical upon which the cylinder can rotate, or rather the origin of my cylinder right there. Similarly, for the coefficient of drag, just a few more things are required: direction of lift, direction of drag, this UFR, and in what axis your pitch essentially will happen. A reference velocity, the reference length and area as well. This will be necessary for initialization as for the calculation of your particular coefficients and the forces on top of that as well. So this concludes effectively what is your vortex shedding. And ultimately we can see the different data points that we were interested in, the power spectral density, the SPL, and subsequently how the vortex shedding effectively is occurring for our particular domain. So this is a plot of velocity with respect to the length away from the cylinder. Essentially what we see here is beyond the cylinder, let's say if we take a line such as this, what is the quantity of pressure, what is the quantity of velocity that's going to look like. We can see that the properties are oscillating, hence describing what our shading frequencies are looking like. If we were to post-process the root mean square pressure value over the certain frequencies that we have, this is PRMS versus the frequency, we essentially get this plot right here. We can see that there are spikes of the frequency that are coming, which align with what our findings have been with respect to the Strohal number that we have calculated and the shedding frequency of 0.1 Hertz. So ultimately there is one thing that you would be interested in is actually having a plot over your particular cylinder to understand what exactly is happening to your pressure plot. Let's take a look at how exactly to do that. So once you have imported the .foam file here, You can either reconstruct or you can do the decomposed. For myself, I have just reconstructed the case in the sense that I've taken the data from the 4 different processors and I've just combined them into one serial thing. Once you have that, you can just select the patch cylinder and have a slice of that cylinder over here. So initially it would look something like this, your surface here, and I just took a slice over this. Right after the slice, you can just do a plot on sorted lines. So the plot on sorted lines is right here, again the control space right here. So the data that we're looking at right here is pressure data that is present on top of my cylinder right here. So you can see the pink dot here corresponds with the location where we are currently at right now. Now, if we want to take a look at the plot itself, we can just do the split screen horizontally and just have the plot here visible, right? Even with the plot, if we are only interested in the pressure, I can just select the pressure right here and you will see that we now have pressure data on top of my entire cylinder, and this is time accurate in the sense that as the time aspect of it increases, we will see a particular spike of the pressure somewhere around right here, and the pressure essentially keeps increasing and decreasing on the top and bottom portions of my particular cylinder. So this also gives you a good representation of what exactly it is, the pressure profile that you are looking at. This also gives you a view of where exactly it is that your pressure or your flow is getting separated from your particular cylinder here. So right where you have pressure 0, there will be a stagnation point. Essentially you will have flow that no longer stays there and it is going into this negative values right there. So this is a great way for you to again understand what exactly it is that the pressure data is trying to tell us over this entire cylinder.
So OpenFOAM has proven itself in its capabilities as a CFD tool. Is it perfect? Far from it. But is it worth giving a shot? Absolutely yes. Uh, I would like to cover a bit more on the concepts of OpenFOAM. Keep coming back to this channel. Perhaps you'll like something that would stick with you. Over the course of a few more videos, I would like to cover a bit more on aerodynamics and a bit of acoustics. Let me know in the comments below what you would like to see next. And until next time, stay tuned.